66 million years ago, life on Earth witnessed its most apocalyptic moment. A killer asteroid, 10 kilometers wide, hurtled toward the planet at a velocity 3 times the speed of a bullet. It struck the Yucatan Peninsula in modern-day Mexico, unleashing a force greater than 10 billion atomic bombs. The aftermath was devastating: global wildfires, earthquakes, volcanic eruptions, and a prolonged darkness caused by thick clouds of debris. This catastrophic event wiped out 75% of life on Earth, including the mighty dinosaurs. Yet, remarkably, some species managed to survive. Tiny, unassuming mammals, our distant ancestors, hid in the shadows, scraped by on scarce resources, and eventually rose to dominate the planet. But what if a disaster even deadlier loomed in our future? A catastrophe not from Earth or even within the solar system, but one born in the fiery crucibles of dying stars. This is the terror of a gamma-ray burst, a cataclysmic explosion so powerful that it could sterilize life across entire galaxies. Could humanity, with its advanced technology and ingenuity, survive such an event? Could we find a way to endure what has been described as the universe's ultimate death ray? This essay explores the dangers posed by gamma-ray bursts, humanity's odds of survival, and the potential backup plans we might devise to safeguard our future. Through a mix of scientific insight, speculative ingenuity, and an appreciation for the wonders of the cosmos, we will chart humanity's possible path through this astronomical trial. Gamma-ray bursts are the most luminous explosions in the universe. They occur when massive stars collapse into black holes or neutron stars, unleashing an incomprehensible amount of energy. These bursts of gamma radiation can last anywhere from milliseconds to several minutes, releasing more energy in that short time than the sun will emit over its entire 10 billion year lifespan. There are 2 primary types of GRBs: short-duration bursts, which last less than 2 seconds, and are thought to result from the merger of 2 neutron stars, or a neutron star and a black hole, and long-duration bursts, which can last up to several minutes, and are associated with the collapse of massive stars. The danger of a GRB lies in its concentrated beam of radiation. If Earth were in the direct line of fire, the consequences would be apocalyptic. Gamma rays would strip away the ozone layer, exposing the planet to lethal levels of ultraviolet radiation. The intense energy would ignite chemical reactions in the atmosphere, producing nitrogen oxides that could blanket the Earth in a toxic haze, dimming sunlight and disrupting photosynthesis. The resulting collapse of ecosystems would trigger mass extinctions on a scale rivaling or surpassing the asteroid impact that ended the age of dinosaurs. Fortunately, GRBs are exceedingly rare. They occur in distant galaxies millions or billions of light years away, and their beams are highly directional, like cosmic sniper shots. For Earth to be affected, the GRB would need to originate within our galaxy and aim directly at us. The odds of this happening are estimated to be about 1 in a million per year. However, there is evidence that a GRB may have already caused a mass extinction on Earth. Around 450 million years ago, during the late Ordovician period, a sudden and severe extinction event wiped out 85% of marine species. Some scientists speculate that a nearby GRB may have triggered this die-off by depleting the ozone layer and exposing life to deadly radiation. While the odds of another GRB striking Earth are low, the stakes are astronomically high. A single event could render the planet uninhabitable. As we expand our understanding of the universe, the question becomes not just whether we could survive a GRB, but how we might prepare for such a cosmic catastrophe. If a GRB were to strike Earth, the effects would be swift and devastating. First, atmospheric destruction. The gamma rays would obliterate the ozone layer within moments, exposing the surface to unfiltered ultraviolet radiation. This would cause severe burns, genetic mutations, and a sharp increase in cancer rates for any living organism exposed to sunlight. Second, chemical fallout nitrogen in the atmosphere would combine with oxygen to form nitrogen oxides, creating a dense reddish-brown smog that would block sunlight. This nuclear winter scenario would lead to a dramatic cooling of the planet, disrupting weather patterns and agriculture. Third, ecosystem collapse. With sunlight reduced and the ozone layer gone, plants would struggle to photosynthesize, leading to a collapse of food chains. Marine ecosystems would be particularly hard hit, as phytoplankton, responsible for producing much of Earth's oxygen, would perish. Finally, mass extinctions. The combined effects of radiation, atmospheric changes, and ecosystem collapse would likely lead to a mass extinction event. Humans, despite our technological advancements, would face significant challenges in surviving the immediate and long-term consequences. To answer this question, we must consider humanity's resilience and capacity for adaptation. While a gamma-ray burst would pose unprecedented challenges, there are several ways we could potentially survive. Firstly, underground shelters. Just as our mammalian ancestors survived the asteroid impact by hiding in burrows, humanity could retreat underground to escape the worst effects of a gamma-ray burst. Subterranean bunkers, mines, and cave systems could shield populations from radiation and provide a controlled environment for survival. There are already numerous underground shelters around the world, such as the Raven Rock Mountain Complex in the United States and the Svalbard Global Seed Vault in Norway. These facilities could serve as starting points for survival efforts. With sufficient warning, governments could expand existing shelters or construct new ones, equipped with life support systems, vertical farms, and energy sources such as nuclear reactors or geothermal power. Secondly, space colonies. One of the most intriguing backup plans for a gamma-ray burst is to establish self-sustaining colonies beyond Earth. The Moon and Mars could serve as safe havens for humanity. While the Moon lacks an atmosphere, its proximity to Earth makes it an ideal location for an emergency colony. Mars, with its thin atmosphere and abundant resources, offers long-term potential for human settlement. Orbital habitats such as those envisioned by NASA and SpaceX could house thousands of people in the event of a global disaster. These stations could be powered by solar energy and sustain life through advanced recycling systems. Thirdly, geoengineering solutions. If a gamma-ray burst were imminent, humanity could attempt to mitigate its effects through large-scale geoengineering projects. Scientists could deploy satellites equipped with reflective shields or aerosols to create a temporary ozone layer, protecting the planet from UV radiation. Technologies could be developed to remove nitrogen oxides and other pollutants from the atmosphere, restoring breathable air and clearing the skies. Lastly, adaptation through biotechnology. Humanity's ability to adapt biologically could also play a role in surviving a gamma-ray burst. Advances in genetic engineering might allow us to develop crops and organisms that can thrive in low-light, high-radiation environments. Similarly, humans could be genetically modified to withstand higher levels of radiation or other environmental stresses. The asteroid impact that wiped out the dinosaurs serves as a powerful case study in survival. While the dinosaurs succumbed to the combined effects of heat, firestorms, and darkness, some species, such as crocodiles and small mammals, managed to endure. Their survival strategies offer valuable lessons for humanity. Flexibility. Species that could adapt to changing conditions, such as mammals with diverse diets, were more likely to survive. Humanity's ability to innovate and improvise could similarly give us an edge in a gamma-ray burst scenario. Resilience. The ability to endure prolonged periods of scarcity and hardship was critical for survival. Developing resilient systems and mindsets will be essential for humans facing a gamma-ray burst-induced apocalypse. Collaboration survival often depends on cooperation. Just as early mammals may have relied on communal living, humanity will need to work together across borders and disciplines to overcome the challenges of a gamma-ray burst. A single gamma-ray burst can release more energy in 10 seconds than the sun will emit in its entire lifetime. The most distant gamma-ray burst ever observed occurred 13 billion light-years away, meaning it happened when the universe was just 600 million years old. If a gamma-ray burst were to strike Earth from a distance of 6,000 light-years, it could still cause a mass extinction. The Milky Way experiences about one gamma-ray burst every 10,000 to 100,000 years, though most are not aimed at Earth. Humanity has always been at the mercy of cosmic forces, from asteroid impacts to solar flares. A gamma-ray burst represents one of the most formidable challenges we could face, a cosmic apocalypse capable of reshaping the Earth and extinguishing life as we know it. Yet our species has a unique advantage, the ability to anticipate, prepare, and innovate. Through a combination of underground shelters, space colonization, geoengineering, and biotechnology, humanity could survive even the most catastrophic gamma-ray burst. The stars that create gamma-ray bursts also forge the elements that make life possible, including the carbon in our bodies and the oxygen we breathe. In a sense, we owe our existence to these cosmic explosions. By embracing our curiosity and ingenuity, we can turn the threat of a gamma-ray burst into an opportunity to reach for the stars, ensuring not just our survival, but our place in the universe.